All right, let's talk about a statistical formula that, a ton of us use without even thinking twice. But what if I told you it has a hidden flaw? A flaw so significant that it can actually lie to you, hiding the very problems it's supposed to help you find. Let's dive in.
I mean, think about it. Whether you're running a massive factory floor or just tracking your daily workout habits, the question is always the same. Is this thing stable, or is something out of whack? How do you separate the normal, everyday randomness, the noise, from a real signal that screams, hey, pay attention to me? Getting this right is absolutely crucial.
So that leads us on this quest for stability. You see, to find a problem, you first have to know what normal even looks like. The whole goal is to measure the natural rhythm, the background hum of a process, so that the second something goes wrong, it sticks out like a sore thumb.
And to do that, statistical giants like Walter Shewhart, W. Edward Deming, and others gave us this brilliant tool called control limits. The idea is pretty simple, actually. You figure out the average of your process, and then you build a fence around it, an upper and lower boundary using this formula: the mean plus or minus 3 standard deviations. Anything that falls inside that fence is just normal noise, but anything outside, that's a signal.
Now, I know what you're probably thinking. Okay, but why 3, right? Why not 2 or 5 or 10 sigma? And you know what? That is a fantastic question that deserves its own deep dive someday. But for today, we're going to accept 3 sigma as the standard and focus on a much sneakier part of the equation: how we actually calculate that sigma.
See, in the real world, we almost never have all the data. It's just not possible. We're always working with samples. So that theoretical formula gets a practical makeover. We use the sample mean, x bar, plus or minus 3 times the sample standard deviation, or S. This is the version we all learned in school, right? Well, this is also where the trouble starts. And that right there brings us to the heart of our story, the familiar formula's flaw. Because it turns out, this trusty old method has a huge weakness. It works beautifully when a process is already stable and predictable, but it can completely fall on its face when you need it the most, when you're trying to figure out if an unstable process is, well, unstable.
So the problem isn't the mean, and it isn't the number 3. The real culprit is hiding in plain sight, right inside the calculation for standard deviation. And it all comes down to one simple bit of math we all do without thinking: the square.
Okay, let's make this super clear with an example. Imagine we've got 4 data points. To get the standard deviation, the first thing we do is see how far each one is from the average. So we've got these small deviations, 2, 4, 3. Pretty normal stuff. But then look at that last one, a massive deviation of 20. That is clearly an outlier, what the pros call a special cause of variation. Okay, now remember the next step in the formula. To get the variance, which is just the standard deviation before you do the square root, we have to square every single one of those deviations. So, just think for a second, what is going to happen to that number 20 when we square it, especially compared to the little guys?
And bam! This picture says it all. 2 squared is 4, 4 squared is 16, 3 squared is 9, no big deal. But our special cause, our outlier of 20, when you square it, it becomes 400. It just completely dwarfs everything else. That one single outlier contributes more than 15 times the variation of all the other points put together.
And that gets to the absolute heart of the flaw. That squaring operation, just by its mathematical nature, acts like a giant amplifier for the biggest numbers. It gives way more weight to the largest deviations.
So what's the big deal? Well, that massive 400 gets tossed into the average, and it blows up the final standard deviation like a balloon. This makes our control limits way too wide. And with the fence that's too wide, future problems that we should be catching can now slip right through, looking perfectly normal. The tool designed to find instability is now actively hiding it. How crazy is that?
So, are we just stuck? Not at all. Fortunately, there's a much smarter way to do this. And that brings us to a more robust measure. We need a way to estimate all this variation that isn't so easily tricked by those big, flashy outliers.
And that method is called the moving range. Now, instead of looking at how far each point is from the overall average, the moving range just looks at the jump from one point to the very next one. It measures the gap between consecutive points, giving us a much better feel for the point-to-point jitteriness of the process.
And the best part is how incredibly simple this is. You just take a data point and subtract the one that came right before it. That's step 1. Step 2, you take the absolute value,
because we don't care if it went up or down, just how big the jump was. And finally, you just average all those little jumps together. That's it. You're done. So why is this the secret sauce for looking at unstable processes? It's simple, really. It completely sidesteps the whole problem from the get-go. There is no squaring operation anywhere in sight. That big outlier of 20 doesn't get amplified into 400. It's just treated like a bigger jump, giving us a much more honest picture of what's really going on.
Now, the method isn't quite perfect on its own. It does have a slight bias. But this is where the hero of our story comes in, an English statistician named L.H.C. Tippett. He figured out the exact correction factor needed to take that average moving range and turn it into a perfectly unbiased and really robust estimate of sigma. So in his honor, we'll call this the Tippett standard deviation.
Okay, let's bring this all home and wrap it up in our final section, the right tool for an unstable world. Because the goal here isn't to just throw out the old formula, but to be smart about knowing when to use it and when to reach for something better.
So here's the bottom line, the cheat sheet, if you will. The classic standard deviation, the one we all know, uses those squared deviations. It's super sensitive to outliers, which makes it great for monitoring a process you already know is stable. But the Tippett method, using simple absolute differences, is robust. It's way less sensitive to those outliers, which makes it the far superior tool for investigating whether a process is unstable in the first place.
And here is the really cool final piece of the puzzle. When a process is actually stable, when there aren't any crazy outliers messing things up, guess what? Both the classic method and the Tippett method will give you basically the exact same answer. They both zero in on the true value of sigma. Which just goes to show the classic formula isn't wrong. It's just a specialized tool that we've been using for the wrong job.
And really, that's the lesson here, isn't it? Being smart with data isn't about memorizing one formula and using it for everything. It's about understanding the strengths and weaknesses behind your tools and knowing which one to pick for the specific job you're trying to do.
So that leaves us with a final question to think about. We just saw how the simple context of stable versus unstable completely changes which tool is best. So, what other standard, one-size-fits-all tools that you use every day might have their own hidden flaws, just waiting for the context to change? Something to chew on. Thanks for tuning in.